Hi, good afternoon everyone. Welcome to Unacademy channel, YouTube classes. Are you able to watch everyone? Are you able to watch? Hello everyone. Are you able to watch? Good afternoon everyone. Hello everyone. Are you able to watch? Good afternoon everyone. Hello everyone. Are you able to watch? Good afternoon everyone. Yes. So you are able to watch right now? So welcome. Good afternoon to all. How are you everyone? So how are you everyone? So today our topic energy stored in capacitors. Are you getting now? Audio video clearly? Are you getting? See? Who are watching here, just you can reply here. Yeah. So today energy stored in capacitor. Topic is energy stored in capacitor. See, in this energy stored in capacitor, previously what we have discussed, combination of capacitors and methods to find. And now, so in this energy stored in capacitor, we have to find how to store the energy in a capacitor. So, and what are the different equations for that energy stored? We'll see that. Okay. So, is anyone there? See, before going to that, okay, first we'll see that. Energy stored in capacitor. See, energy stored in capacitor. Generally, capacitor means what? We can take the parallel plate capacitor. It consists of what? One is positive and one is a negative plate. Okay. So take a parallel plate capacitor and see earthing it. So that what? More capacitance it has, means it can store the more charge. See, generally we have to store the charges, means we have to move the charges into the capacitor, right? From 0 to small q, capital Q charge we have to move. So for moving what, we have to apply some force so that work will be done because of the displacement. That means work done will be what? Stored as here energy. Suppose a small amount of charge dq. Okay, a small amount of charge dq is moved into the capacitor with potential V. So that what is the work done due to the small charge? Potential into dq, because potential is what? Work done by charge. So dw is V dq. Actually V equal what? Q by C. right? Because Q equal to CV. So V equal to Q by C or C equal to Q by V. This is a small work done. To get the total work done from what 0 to total charge capital Q, we have to integrate this. So integrate now. Integration 1 dW is W. It is equal to C 1 by C constant integration of Q dQ 0 to capital Q. Q dQ is Q square by 2. Absolute upper and lower 0 means no need. So it will be Q square by 2C. Or you can take Q equal to CV. C square V square by 2C. CC get cancelled. 1 by 2 CV square. Okay, now? Or in another form, so another one. Suppose see Q square by C equal what? Q by V. Q2 get cancelled. QV by 2. So this work done is what? Stored as nothing but energy. That is Q square by 2C or half CV square or half QV. This is the energy stored in capacitor. This work done is what? Stored as the capacitor. Suppose see if number of capacitors are in series. In series combination we have what? Charge is constant, right? So you can take U equal to Q square by 2C. Then U1 is 2, U2 is 2, U3 so on. What will you get? See 1 by C1 is 2, 1 by C2 is 2, 1 by C3 so on. Right? Because Q square by 2, Q square by 2 get cancelled. Eh? Now in parallel what? V is constant potential. So U equal to half CV square. V constant. Eh? So therefore U1 is 2, U2 is 2, U3 so on equal to see C1 is 2, C2 is 2, C3 so on. This is ratio, energy stored ratio. Next, energy density. See, energy density mu. How can you take energy per unit volume? Okay, so we can take half CV square by volume. Okay. What is C here? Capacitance of parallel plate capacitor. Epsilon naught A by D. Into. See, what is the potential? We have the relation electric field into distance. Okay. Just wait, guys. Are you able to getting now? We have relation now, potential or electric field equal to the negative gradient of the potential or E equal to V by D in uniform field. So E equal to ED whole square by volume is what? Area into thickness. Let's see, all will get cancelled. What will get? Half into epsilon E square. So energy density mu equal what? Half epsilon E square. Or epsilon means what? K epsilon naught. K E square. That one, see? Epsilon E square. See, D square get cancelled. A get cancelled. All will get cancelled. This is the energy density. Energy per unit volume. Okay? Are you getting right? Right, very good. Hey. Chaitanya College. Hi. Your name? Okay. Now see, in this energy stored in capacitor, we have applications. When a dielectric is placed between the plates of a parallel plate capacitor, what about the energy stored? See, generally dielectric means Bhavani. Hi. Kaushika. Okay. Hi, Kaushik. Hi, Kaushik. How are you? Hi. You are not coming to classes. Okay. See, dielectric or dielectric constant means it is like what? Insulated. That means, see, if you place this dielectric material in between the plates of capacitor or plates of that terminals of battery, what will happen? Electric field will be decreases by 1 by k times, and potential also decreases by 1 by k times. Charge also decreases by 1 by k times. Mainly we can take this, right? But here the capacitance will be increases by k times. Capacitance what? Increases by k times. Capacitance. Charge will be what? New charge q into 1 minus k. Decreases. But mainly capacitance is what? K times increases capacitance. Kaushik, are you there? Are you there, Kaushik? Are you there now? Okay. So capacitance will be here what? Increases by k times. But potential and electric field, sorry. Are you there? Yes, are you there now? See how capacitance here increases. So how it is increasing means, first of all, what is electric field for a conductor? Sigma by epsilon naught. So charge density also decreases when dielectric places na. Sigma will be what? Sigma naught minus sigma I, induced charge density, by epsilon naught. It is equal to what? Sigma naught by k times. 1 by k times decreases na. Right? Or we can write k epsilon naught is epsilon also. And potential is what? E into D. So what is E here? Sigma naught by k epsilon naught into D. Okay. And what is sigma here? Q by A into D by k epsilon naught. This is V. Now capacitance C equal to what? Q by V. So Q by QD by Ka epsilon naught. Q cancel. K epsilon naught A by D. Actually it is what? Initial. So C equal to K C naught. So capacitance will be what? Increases by K times. Always. Okay. Capacitance will be increases. Now in this energy, this parallel plate capacitor, due to this dielectric, energy stored will be different. How it is different here? For example, see, to a capacitor, what we have to connect to battery now. Suppose in between the plates of capacitor, between the plates of capacitor, you can keep the dielectric constant K. Okay. The potential C naught. So first of all, introduction of dielectric without disconnecting. Battery is what? Without disconnecting means battery is connected. See, when battery is connected na, potential continuously supplies and potential becomes constant. V equal to V naught, constant, because of maximum it will get. But the capacitance will be what? Increases by K times. Capacitance will be increases by K times. Okay. Potential becomes constant. So potential becomes constant means we have to take what? U dash equal to. See, initially of C naught V square. So of C V square. Half into K C naught into V square. See, K into half C naught V square is U naught. So energy will be what? K times increases. K times what? Increases. Now disconnected. So battery is disconnected now. See, whenever battery is disconnected, charge becomes decreases and becomes constant. So charge constant, but capacitance is what? Increases only. 3 times. Means dielectric is placed only. Okay. Now charge constant means we have initially C naught equal to Q naught square by 2C. Q or Q naught constant. So finally U dash Q naught square by 2C. C means K C naught. See, 1 by K into Q naught square by 2C. That is U, it is U by K. So energy will be what? 1 by K times decreases. Okay. Energy 1 by K times decreases when battery is disconnected. Okay. When battery is disconnected, 1 by K times decreases. When battery is connected, K times increases. Energy will be. Okay. So this is about energy stored. Okay. Now in this only we have redistribution of charges. What is that? Redistribution. Redistribution means capacitors are directly connected without battery. See, this is one capacitor. This is another capacitor with the same terminals. Negative plus, positive plus, C1, C2 are connected directly. Is connected in parallel. Okay, now. So here something like switch. So connected like this. See here charge Q1, here charge Q2. Whenever they are connected directly, what will happen is the common potential V you will get. V will be what? Common potential. And what about the total charge according to conservation of charge? Here Q1 in C1, Q2 in C2. So Q equal to Q1 plus Q2. Okay. So what is Q here? They are in parallel. So total C and C1 plus C2 into total potential V equal to Q1. C1 V1 plus C2 V2. So that common potential V will be what? See? C1 V1 plus C2 V2 by C1 plus C2. Okay. This is the common potential. Very important. C1 V1 plus C2 V2 by C1 plus C2. Let's see what is the loss in energy. Loss in energy. What is the loss in energy? Final minus initial. What is the final here? V final of C1 V square plus of C2 V square. That is half into C1 plus C2 into V square. And what about initial of C1 V1 square plus of C2 V2 square? So now, what is it? Change. Therefore, delta U equal what? Final minus initial. What is that? Half into C1 plus C2 into V square minus half into C1 V1 square plus half into C2 V2 square. So, you can solve this. You will get 1 by 2 C1 C2 by C1 plus C2 into V1 minus V2 whole square. Loss in energy. Very important. Suppose see, in first case for negative, positive connected. Suppose if they are interchanged, positive plate is connected to negative plate. Interchange. In that case, what you will get? Opposition. V will be what? C1 V1 difference, C2 V2 by C1 plus C2. Then energy stored will be what? Delta U equal to R C1 C2 by C1 plus C2 into V1 plus V2 whole square. If potentials are not equal, then charge can be flows. This is about energy in opposite terminals. Okay. Suppose here, take two conductors. We will take what? Conductors, spherical conductors. Take spherical conductors. So if two spherical conductors having the charge A, capacitance C1 is connected through a wire with another spherical conductor Q2 having charge is uniformly distributed. It is B. A charge Q2, a charge Q1. See, whenever they're connected now, what is the energy? First of all, what is the charge Q1? C1 V1, and in Q2 is C2 V2. Now after connecting what, Q1 dash equal to C1 V, V will be potential, common potential, V2 equal to C2 into V. Now see what is the ratio, Q1 dash is to Q2 dash, C1 is to C2. Okay? Actually for spherical conductor, C equal to what? 4 pi epsilon naught R. So C proportional to R. So therefore Q1 dash is to Q2 dash equal to R1 is to R2. You know? R1 is to R2. And see, the conservation of charge final is what? Q1 dash plus Q2 dash equal to initial Q1 plus Q2. So what is Q1 dash? C1V plus C2V equal to C1V1 plus C2V2. That is V equal to, already we know, C1V1 plus C2V2 by C1 plus C2. See, C proportional to R now, so we can write R1V1 plus R2V2 by R1 plus R2. So what about effective capacity? C effective Q by V. Q equal to Q1 dash plus Q2 dash by common potential V. So that we can write Q1 dash by V plus Q2 dash by V. That is C effective will be what? C1 plus C2. Means they are in parallel combination. Now loss in delta U equal to what we have? Of C1 C2 by C1 plus C2 into V1 minus V2 whole square. Or if you substitute C equal 4 pi epsilon naught, it will get off into 4 pi epsilon naught R1 R2 by R1 plus R2 into V1 minus V2 whole square. This is about what? Loss in energy. So like this we have different applications are there. Just right. We'll see one more important case. Okay. See guys. Suppose see, let n number of identical liquid drops, each radius smaller, are combined to form a big drop of radius capital R. Then we have some relations. See here, each charge is Q, capacitance is C. To become what? Big radius, big liquid drop with radius or capacitance C. Then what will change? First of all, here what is constant? Volume is constant, right? So how many here? N into V equal to here total volume. N into see 4 by 3 pi R cube equal to here 4 by 3 pi capital R cube. See capital R cube equal to N into small R cube. that is capital R equal n power 1 by 3 into R radius. And what about total charge? N into Q. Yeah? And now what is the capacitance? New capacitance 4 pi epsilon naught into R. That is 4 pi epsilon naught into what is R here? N power 1 by 3 R. So n power 1 by 3 into 4 pi epsilon naught R, that is C, small c. C dash into. Okay. Potential we got. Capacitance we got. Potential V dash equal to Q by C dash. So Q is NQ, C dash is N power 1 by 3 into C. So Q by C is V initially. So N power 1 minus 1 by 3, N power 2 by 3. So V dash equal to N power 2 by 3 into V. Okay. And what about energy stored? See, initially U equal to we have Q square by 2C. Small q square by 2C C naught. U dash is what? Capital Q square by 2C dash. What is capital Q square? N square Q square by 2 into. What is C dash? N power 1 by 3 into C. So Q square by 2C is initial U. So N power 2 minus 1 by 3, 6, 5 by 3. So U dash will be N power 5 by 3 into U. And surface charge density. Initially sigma Q by 4 pi small r square. Sigma dash capital Q by 4 pi capital R square. See N into Q by 4 pi into capital R square. N power 2 by 3 into R square. So 1 by 3. Q by 4 pi square is sigma. So sigma dash equal to we will get what? N power 1 by 3 sigma. So like this we can find very important application it is. Got it now? Okay. So remaining we'll see in the next class. Okay. Bye, I love you.